Good afternoon, everyone. Welcome to our pre-lab lecture. Our experiment today is lab number 8, an introduction to acid and bases, which I believe you have covered in the lecture. Acid and bases, this is, I believe, chapter 16. And by now, you should have covered the concept. I want to share my screen and real quick, maybe just walk you through the uh, lab procedure, how you will collect the data for this experiment. I won't spend a lot of time going through the background definition of an acid, definition of a base according to Arrhenius, according to Bronsted-Lowry, and there is also Lewis base definition, Lewis acid base definition, which is transfer of electron pair donor, electron pair acceptor. That's something you should know for your lecture. To get you started with, you need to access the, you'll have to access the module, all right, module number 8. There are some resources which I want you also to watch during your own free time. The definition of a power solution, and in particular, the titration curves and definition of the titration. You have done that in Chem 1. You may have had hands-on experiment on titration of an acid of a base, but in Chem 2, this course you should extend that knowledge, that concept of acid-base titration to generation of calibration curve. Typically, there is a strong base, a strong acid. I've used here a SP for strong base. That means what goes in the puree. Let me see if I can share my whiteboard. In titration, of course, there is a class, where tool class called this the puree, and what goes in here and what you have in a receptacle here is the analyte, or what you are analyzing, and this is the standard. Basically, in acid-base titration, neutralization take place, all right? An acid and a base react, and of course, the two product is salt and H2O. Acid-base neutralization produces an ionic compound or salt and H2O. Now, there are 4 curves, all right? There is a strong acid, strong base curve, which you should have, look at that. I know you know that, where there is point of inflection, or the point where there is a stiff curve. When you have pH on the y-axis, and here is the volume, all right, volume of titrant. Titrant is what goes in the puree, or the standard. pH, all right, changes depending on, this is strong base, strong acid, titration curve, strong acid, strong base titration curve. Maybe I should include the title here, because you'll generate calibration curve as part of the data to submit, and you should follow all the guidelines in generating the curve. Right now, you are expected to generate a curve to communicate some scientific information. And if you don't label everywhere, assuming that, the instructor will know, you may lose point. It's assumed that you are communicating scientific knowledge or information to somebody, and you should have all the signature key features on your curve. For example, the title in this case is titration of strong acid with, you are titration strong acid with strong, that is the title of the graph. All graphs should have a title. Now, for strong, when I say strong base, weak acid, all right, there is a characteristic feature for that graph. You should know that. And then there is weak acid that goes in the puree versus a strong base. This goes in the picker. The one at the first one indicate what you put it in the puree. And there is, of course, the weak acid, weak base, all right, and then weak base, weak acid. What I'm giving you here is you should know how the graphs look like, for this quiz, I only requested you that you should know the titration curve. You watch, you know how it look like for strong base, which goes in the puree, and for strong acid, which is now on the receptacle. And strong base, weak acid, which is now what we are going to do in this lab. What goes in the puree for this lab, we will titrate weak acid or strong base versus weak acid. This is what will go in the puree, all right? You'll have sodium, I think 0.100 molar NaOH. This will go in what? This will go in the puree, and the acid, okay, will be in some receptacle there. Instead of using the indicator to, you know what an indicator is, it's an organic molecule which changes color to signify the equivalent point. You know, when we say equivalent point is a point on titration curve where, let me just show you that. Equivalent point here is point on titration curve where the number of moles, the stoichiometrically equivalent number of moles of the titran and the analyte, what goes in the puree and what goes in the picker. It is theoretical point, but endpoint, all right, endpoint is a point in titration where there is a significant change in color when you use an indicator. An indicator shows the endpoint, hypothetical point that you have equivalent. So basically, this is the theoretical, but in the endpoint, it is a point where there is a significant change in color, and it is shown by what? By the indicator. Now, so in our titration today, we will have a weak acid, and the point here is we will determine the Ka. Objective for this lab is one, determine Ka of a weak acid, all right? Determine the Ka of a weak acid, and it is not, we are not given the concentration of a weak acid. In this case, if we know the weak acid from this equation, generic equation, aqueous plus, or in liquid H2O, all right, in dynamic equilibrium, doesn't want to go to the product side to produce hydronium ion aqueous plus conjugate base. I know you can say if we know the concentration of hydronium and concentration of the conjugate base of the concentration of the weak acid at the equivalent point, we can find the Ka. This is not the case. I don't want you to think that this is what I learned in class and I should use this. No, I know you can use this to calculate, but experimentally, we will determine the what? The Ka over weak acid. And then once we find the Ka, we will identify the acid we have or you will be working with based on the Ka value. Based on the Ka value. How? All right. In titration of a weak acid, strong base versus weak acid, the graph doesn't go like the way you saw in the strong acid, strong base. It might go like that, and then it goes like that. All right. Now, what I want to point here, let's just put here pH, and then here is the volume in ml of titron. As we add the titron from the puree, the pH keeps on changing. The pH keeps on changing. Now, how are we going to use the titration curve? Here is the equivalent point. All right. This is what we call the Pava region. You know what a Pava is? I asked you to read about Pava. Pava solution is a solution that resists change in pH, a solution that resists change in pH because it can both an acid and it has a base, a weak acid and a weak base. It resists change in pH. So here is the Pava, we call this Pava what? Region, Pava region. If you look at if we know the equivalent point, if we can perform the titration today using the simulation, not working with the chemical reagent, if you were to come to the lab and then we will physically fill the puree, perform the titration, go home and generate this crab, but we will electronically generate the calibration curve for a strong base, which will go in the puree, and a weak acid, which will be our analyte. Of course, you look at this region, there is it's gonna rise gradually and then it's gonna flatten out. It's not going to go the way we saw in strong bases, strong acid. It turns out that, all right, it turns out that from Anderson-Hasselbalch equation, you know Anderson-Hasselbalch equation, pH over solution is determined from pKa plus log of what? Log of weak base of weak what? Weak acid under Anderson-Hasselbalch equation. Now, if we can adjust this, if we can adjust the concentration of a weak acid, weak base in such a way that it is 1, log of 1 is 0, log of 1 is 0. So we make that 0. If this is 0, this means pH equals to pKa. pKa. I mean to say this is pKa. pKa. It turns out that at a half equivalent, write this down, at a half equivalent point on the titration curve for a strong titrating a weak acid using strong base at a half equivalent point, pH equals to pKa, equals to pKa. Let me go back to the previous slide on my whiteboard, that if we end up with, all right, if we end up with the titration curve like this in our simulation, and we determine the what? The equivalent point. And then we can determine the pH at a half equivalent point. In other words, let me give you an hypothetical situation here. If uh, volume of titron at equivalent point equals to 10. In other words, here, if I have my equivalent point right here, let's say here is 10, and I'm using the arrow, you'll also use the arrow to indicate which is your equivalent point. I'm using that as 10.0 ml, 10.0 ml. If that is the equivalent point, I have equivalent point, all right, at a half equivalent point, V of the titron here is 5 ml. So I'll say, what is the pH at 5 ml? So I'll just go to my graph, if I have the data, I'll say at 5 ml, if 5 ml is right here, 5 ml is right here, what is what? What is the pH? What is the pH at 5? And then your pH is the same as the pKa from Anderson-Hasselbalch equation, Anderson-Hasselbalch equation. And from there, if you know the pH, which turns out that pH equals to pKa, you know the pKa. The relationship between pKa and Ka is pKa equals to negative log of Ka, or Ka equals to 10 raised to negative pKa. So from here, you can, if I'm given different acid with their different, either their pKa value or either their Ka value, I can identify the acid. I can identify the acid. So the objective for this lab is to identify, perform the simulation of titration, and then identify the acid. Uh, I will walk you through the simulation, the Excel spreadsheet, which you will have to download. And the instruction is, if you make a mistake, please discard the already downloaded what? Downloaded spreadsheet, come back again to Canvas and download. Don't save or don't continue if you make a mistake. It is safe to start over again, This is where all right, this is where the spreadsheet is, if you look at this, but this is just a document. You know, you can come back for background information on acid-base titration. I hope you read this relationship between Ka, Kp. It's part of what I wanted you to read before coming in today. I know you know how to find the Ka Anderson-Hasselbalch equation, the power region. This is what I was talking about, that at a half equivalent point, all right, somebody was using maybe 21 or 22, and then half equivalent point, if we know the pH, we can conclude that the numerical value for pH at a half equivalent point is the same as the pKa, and then we move on from there to determine the Ka and identify the acid. It's the same acid we have here. Let me just show you the Anderson-Hasselbalch equation. All right, conjugate base of the remaining acid. If we change this to 1, log of 1, if concentration of both species are the same, log of 1 is 0. That's what that means. The types of acid we have, all right, this is the background on how you will do. I know when you read this, it might not really make sense to you. I will load, all right, I will load the, I will load the spreadsheet download and walk you through this direction. Just pretty much straightforward. Let me go back to the module right here. This is what you need to download. I'm gonna download. I know. Okay. So now what you're seeing is the spreadsheet of simulation of titration. I had to blow it up because, you know, if I split the screen into two, you may not be in a position uh, to read. So at the outset, these are the drop down menu here. These are the assets you will have to see if what we are working is 2-chloro benzene or acetoacetic acid or 4-chlorobenzene or benzoic acid based on their Ka value, based on their Ka value. So one of them, all right, one of them should give you the positive test for which acid we are titrating. This is the weak acid. It's just a simulation that this is the proof for the pH meter magnetic starter to start the solution, make it homogeneous. And you know, on the screen of the pH meter, some you may see the curve being generated, or you may want to collect the data. This is the case for today. You will collect the data and use the spreadsheet to do what? To generate the calibration curve similar to what you will see here. Now, the direction called for, you know, if you look at starting here, look at where the cursor key is. It's 0 at 0, 0. That is the pH of this solution. It's assumed that it is inside. This is an acid, you know. Acid turn blue litmus paper to red. It's acidic right now. And the pH is around maybe 2.8, 2.9. The lower it is, the more acidic it is. You'll see when we add NaOH, this is the titration we will be using, NaOH. The data which will be used will be generated here. The addition of, this is where you will add. You see where the cursor key is? If I say 1 ml, you'll see this pH value will change, and the amount of NaOH added will just keep on increasing. So let's add 1 ml. So let me reset and see if it's gonna give me, yeah, you see when I add 1 ml, there is volume increment here and the pH increase. So I'll keep on adding 1 ml, 1 ml, 1 ml. You see every 1 ml, the pH, the volume of NaOH added is just like the meniscus is dropping. It is dropping as we add NaOH. So you don't have to type in every time. You have to click one. I click one. If you look at the graph, it keeps on changing, going up and up. So I'll keep on adding. So let's just real quick. I will keep on adding one. All right. At some point, there will be a jump. Yeah, you see it's jumping now. You may want to continue for until you have, you know, no more changing, or until the end, whichever way you want. I think that is the maximum we can go. We can go to 50 because our point of interest is the equivalent point here. Please, I don't want you to just cut and paste this and say this is what I have for my graph because I will need this graph as well. So you will use the data here. You can copy the data you have here. On a brand new workbook on Excel, you will generate your own curve, not the one you produced during the simulation. And look at the characteristic feature, all the signature. I want to see the title of the graph. I want to see the y-axis label. I want to see the x-axis label. Volume mean what? Is it in liters? Volume mean what? Titron is what goes in the purette. Remember that. You should use at least 3/4 of the page. I don't want like a really tiny graph that I can't even see the volume. You have to scale it in such a way that you don't end up with a small graph. This is one graph I will be looking at for part A. This is the graph we will be looking at. So if you look at going back to the direction, I think for part A or part 1, that is what it was. For part 1, that is what you had to do in part 1, which shouldn't be hard. You see this? Finding the equivalent point of the unknown asset. We don't know which asset we are dealing with. It could be any of those assets given in the spreadsheet. The point is to know that I have equivalent point in order to get the what? The pKa. From my simulation, all right, from my simulation here, you cannot hypothetically and say, all right, equivalent point is 30 and our equivalent point is 15 here, and maybe pH is 3.5. There is another graph you need to generate, all right? You need to generate for determining the equivalent point, and then we have it now, the equivalent point. It is like fine tuning. This is not really the graph you will use to determine the equivalent point. This is just an hypothetical that we know if the equivalent point is at 30, we will perform 20 titration around the equivalent point and 20 titration around a half equivalent point. So if we know equivalent point is 30, half equivalent point is 15, we'll perform 20 titration around a half equivalent point here. But first, A is pretty straightforward. I know you can find A to get the equivalent point. Now for part P, you will having now established, all right, having established the pH at the equivalent point, you will analyze and say, what is half? You see somebody was using 12 as the equivalent point. Half equivalent point is 6. So around 6 and around 12, we will have to perform. Let me just see if I can use the 30 we generated, all right? The 30 we generated, remember it was something like this, all right? And we had around here 30. So a half equivalent point is 15. What this means in a half is if 15 right here, we will add 0.1 around 14 right here, all right? 14, all right, 14, and these will be 16, and then 30 going to what 31, and coming down here 29. So you're gonna have 2 ml In this region, you'll add 1 ml, 1 ml, that is 2 points within half equivalent, 2 ml within half equivalent, and 2 ml within the equivalent. Within this region, you'll perform 20 addition. And then here is 20 addition, 20 addition of 0.01, which is 2 drops. You'll have to add 20 within that region, okay? You're gonna add that within that region. So that is what you will do for, that's what you will do for the a half equivalent point, and that will make sure that things are working on your, for part P, You will now, all right, you will now use these two values to calculate the equivalent point. Once you figure it out, I have the equivalent point and perform that, you'll perform you'll generate the derivative curve to find the equivalent point. So this graph right here is determined from, I have the equivalent point, and in this case, you'll have to use the pH around the equivalent point. This means you only have to use this region right here, the equivalent point. This is the point where you will have to use to generate what? To generate the second derivative. This value at half equivalent point, all right, at a half equivalent point, pH equals to pKa. And how are you going to get that? You'll perform fast derivative graph for this. So what will happen here is you'll have the graph for what? Graph for having that. Let's see. To make this graph, you'll use this graph right here is coming from what? Coming from the volume of NaOH, all right? This is the volume of NaOH for fast derivative. You'll find the pH, this is 1 ml. Now, change in pH and change in volume, this minus this, in this case, there is no, 3.0, there is nothing to change with. So 4.47 minus 3.97 is 0.5. 4.97. Every time you go across, you're subtracting the previous value from the previous row. 4.97 minus 4.47 is 0.05. If you look at this go across here, this is 5.47 minus 4. You call this. This will how you generate change in what? Change in pH. 10.62 minus 10.17, you cannot get that. That's how you get the change in pH. Now, change in volume is the same thing that we don't have anything to subtract with 9.0. So 9.40 minus 4.1 is 0.1. 9.50 minus that's gonna give you that. So how you change. This change in volume is from this column right here. Change in pH right here is coming from this column. So if you have this and that, you'll find the average volume. Average volume is this plus this is gonna give you, and then you divide by 2, of course, change in average volume. This 9.40 plus 9.30 divided by 2 is what we have here. 9.40 plus 9.50, these two right here it will give you the average. You divide by 2. Each time you divide by 2, you are adding and dividing it by 2 to get the average. So once you have this now, we almost there in finding the first derivative data to find the equivalent point. Average, if I divide this and that, that is what you get here. 0.5 divided by 0.1, that is what you have here. Change in pH over change in volume. This will be on your y-axis. This will be on your y-axis, change in pH over change in volume. And here is the average of volume in ml. So this is how the graph will look like. You'll have something similar to this. And just to give you, and what will give you here is the volume equivalent. Look at what I'm doing. I'm using an arrow to indicate where it is. If it is 10, 20 ml, then I know a half of 10 is 5.00. So what is the pH at? pH at 5 ml will be your pKa. So in other words, you will use what? You will use the first derivative. This is first derivative. First derivative what? First derivative graph, to find the equivalent point. And from here, of course, once you know the pH, you can find the Ka, and your job is to identify which acid is in it. If you look at this is the first derivative. If you don't include this line right here, this is the equivalent point. A half of this is your pKa. If you don't include this iron, then you lose some points for no reason. So remember, the pKa you'll have to, or the Ka value for each one of them is given here. This is the pKa. You see this across, if I go across the black numbers here is the pKa, which is of course the same as the pH. So if my pH at a half equivalent, look, if my pH at a half equivalent is 4.190, then I know that is the pKa of my acid, and the acid I'm dealing with is benzoic acid. If the pH at a half equivalent point is 4.760, and then I know the pKa of the acid is the same as the pH, and the acid we are titrating or you are titrating is the acetic acid. So in other words, these are the values you will determine or identify the acid, and that's all what I wanted you to know. Is there any question before we break for the quiz? Any question?
I do have a question.
Yes.
It's not particularly on this lab. It's actually on last week's lab.
Yes.
Now, for the run 1 through 3, did you have a particular molarity you wanted us to start off with?
No. Any can work. Any can work. Any initial concentration of iron 3 ion, that is Fe3 positive, and thiocyanate ion SCNCN, whichever way you stand at the end of the day or at the end of the reaction, you will have the equilibrium concentration for the 3 species to find the KC or KEQ.
Okay, perfect. Thank you so much.
All right, you're welcome. But remember to take a picture of your screen, all right?
Yes, sir. I did do that.
All right.
I already turned it in and everything. I was just making sure I did it right.
All right, that's it. Any other question? If there's no question, we're just gonna break. We have right now it is 1:39. So around 2:30, that is 20 minutes. Around 2:15, you should be done with the quiz. I have to make it available right now. I'm just gonna. You don't have to be in the Zoom, all right? You don't have to be in the Zoom while taking the quiz. You don't have to be in the Zoom. So quiz number 8. Introduction to acid and bases. All right. So
Pardon me, sir.
yes.
I may have misheard. When is the quiz starting?
Oh yeah, I'm just setting it right now. Yeah, I'm just making it available right now. Okay.
Okay, thank you very much.
Yes. So it's now around 2:25. Yeah, I'm setting it right now. Make sure that you can access. Right now, it's not. Should be available now. Go to quizzes. Please go to quizzes and make sure you can access the quiz.